Welcome to the lesson on the flatness tolerance. Your goal for this lesson is to interpret the flatness tolerance. When you're finished with this lesson, you should be able to describe the terms flatness, derived median plane, and flatness tolerance. Describe the tolerance zones for a flatness tolerance. Describe rule number 1's effect on flatness deviation. Describe the modifiers that may be used in a flatness tolerance. Recognize when a flatness tolerance is applied to a planar surface or a feature of size. Describe real-world applications of a flatness tolerance. Interpret a flatness tolerance applied to a planar surface. Interpret a flatness tolerance at RFS applied to a feature of size dimension. Interpret a flatness tolerance at MMC applied to a feature of size dimension. Understand flatness verification principles. Describe how to verify a flatness tolerance applied to a planar surface. Describe how to verify a flatness tolerance at MMC applied to a feature of size. It will take approximately 20 minutes to complete this lesson. Take a look at the new terms introduced in this lesson. It's important for you to know these terms in order to understand the flatness tolerance. Y14.5 defines flatness as a perfect plane. Flatness is the condition of a surface or derived median plane having all of its elements in one plane. Take a look at the example of flatness of a surface shown in this figure. A derived median plane is an imperfect plane formed by the center points of all line segments bounded by the feature of size. The line segments are perpendicular to the center plane of the unrelated actual mating envelope of the feature of size. You can see an example of a derived median plane in this figure. The condition of flatness applies to a planar surface, feature, or to a feature of size dimension, derived median plane. For a part surface to meet the condition of flatness, it must have all of its elements in one plane. For a feature of size dimension to meet the condition of flatness, it must have all of the points of its derived median plane in one plane. However, because flatness, the perfect condition, cannot be produced, it's necessary to specify some allowance for flatness deviation.
Flatness is the condition of a surface or derived median plane being between two parallel planes. You're correct. A derived median plane is an imperfect plane formed by the center points of all line segments bounded by the feature of size. You're correct. Click the right arrow to continue.
A flatness tolerance is a geometric tolerance that defines the allowable flatness deviation permitted on a planar surface or derived median plane. This figure shows you an example of a flatness tolerance. A flatness tolerance is categorized as a form control. A flatness tolerance is one of the 4 direct form tolerances. It never uses a datum reference. It can only be applied to a single planar feature or single planar regular feature of size. A flatness tolerance zone is the space between 2 parallel planes. Take a look at this figure, which shows 2 flatness tolerance zones. The tolerance zone for a flatness tolerance is the space between 2 parallel planes. The distance between the planes is equal to the flatness tolerance value. If a flatness tolerance is applied to a surface, the high and low points of the surface must be within the tolerance zone. If a flatness tolerance is applied to a feature of size at RFS, the median plane must be within the tolerance zone. If a flatness tolerance is applied to a feature of size at MMC, the tolerance zone can be viewed 2 ways. As 2 parallel planes within which the derived median plane must be located, as a virtual condition boundary that the feature of size may not violate. In this course, we'll use the virtual condition boundary interpretation. A part surface may have any type of form deviation within a flatness tolerance zone. 2 typical form deviations are waviness and warping.
Flatness tolerances use different tolerance zones for surfaces and derived median planes. You're correct. The tolerance zone for a flatness tolerance is the space between 2 parallel lines. You're correct. Click the right arrow to continue.
Whenever rule number 1 applies to a planar regular feature of size, it invokes an indirect flatness deviation requirement on both surfaces. This requirement is the result of the interrelationship between rule number 1, perfect form at MMC, and the size dimension. Where the feature of size is at MMC, both surfaces must be perfectly flat. As the size dimension departs from MMC, a flatness deviation equal to the amount of departure is permitted. Since rule number 1 provides an indirect flatness tolerance, you should not specify a flatness tolerance unless it's a refinement of the size tolerance. This figure illustrates an example of how rule number 1 affects the flatness deviations of the surfaces on a feature of size. Whenever rule number 1 applies to a planar regular feature of size, an automatic flatness deviation requirement exists for the derived median plane of the feature of size. This automatic requirement is a result of the interrelationship between rule number 1 and the size dimension. Where the feature of size is at MMC, the derived median plane of the feature of size must be perfectly flat. As the feature of size departs from MMC, a flatness deviation equal to the amount of the departure is permitted. Take a look at this example of the effects of rule number 1 on the median plane of a feature of size. If the limit of the flatness deviation provided by rule number 1 is sufficient for the function of the application, there's no need for you to specify a flatness tolerance.
When rule number 1 applies to a planar feature of size, it limits the flatness deviation of the derived median plane to You're correct. The maximum flatness deviation is equal to the difference of the limits of the size dimension. Click the right arrow to continue. When rule number 1 applies to a planar feature of size, it limits the flatness deviation of both surfaces to You're correct. The maximum flatness deviation is equal to the difference of the limits of the size dimension. Click the right arrow to continue.
This chart shows the modifiers that you can use in a flatness tolerance application. It includes their effects and examples of functional applications where they could be used. It's important for you to be able to determine whether a flatness tolerance applies to a surface or to a feature of size dimension, because the interpretation of each is different. This figure shows an example of a flatness tolerance applied to a surface and a feature of size. The location of the flatness tolerance indicates what it is applied to. Where the leader line of a flatness tolerance is directed to a surface or attached to an extension line from the surface, it indicates that it applies to the feature, surface. Where a flatness tolerance is located beneath or beside a size dimension, it indicates that the tolerance applies to the feature of size.
Which modifier cannot be used in a flatness tolerance feature control frame? You're correct. The projected tolerance zone modifier cannot be used in a flatness tolerance feature control frame. Click the right arrow to continue. Which flatness tolerance applies to a feature of size? You're correct. The flatness tolerance designated with the A is associated with the size dimension, so it applies to a feature of size. Click the right arrow to continue.
Common real-world applications of flatness tolerances are sealing. When using a gasket for sealing, a flatness tolerance may be used in the mating surfaces to ensure the gasket will be able to seal properly. Support. When load distribution or support is important, a flatness tolerance may be used to ensure the distribution of load on the surface. Appearance. When appearance is important, a flatness tolerance may be used to improve the appearance of the product. Measurement repeatability. When a surface is used as a datum feature, a flatness tolerance can be used to qualify a surface for measurement repeatability. Assembly. Where features of size are designed to assemble, a flatness tolerance can be used to establish a virtual condition, acceptance boundary, to ensure assembly. Reducing costs. In some cases, a flatness tolerance may be used to override rule number 1 to allow for larger form tolerance, which reduces manufacturing and inspection costs.
A real-world application of a flatness tolerance is to limit flatness deviations on mating surfaces in a gasket joint application. You're correct. Click the right arrow to continue.
In a flatness tolerance applied to a surface application, 3 requirements must be met. Size, rule number 1, flatness tolerance. The size dimension requires that the actual local sizes and the rule number 1 boundary be verified. The flatness tolerance requires that the flatness deviation on the bottom surface be verified. Let's take a more in-depth look at each of these requirements. The size requirement is met by ensuring that each actual local size is within the limits of size. The size should be measured in multiple places on the feature of size. Next, let's look at the rule number 1 requirement. Where a flatness tolerance is applied to a surface that is associated with the size dimension, and rule number 1 applies to the size dimension, the flatness tolerance value must be less than the size tolerance. Where a flatness tolerance is applied to a surface that is associated with the size dimension and rule number 1 does not apply to the size dimension, the flatness tolerance value may be larger than the size tolerance. Where a flatness tolerance is applied to a surface, the following conditions apply. The tolerance zone is the space between 2 parallel planes. The tolerance zone may be oriented to best fit the high and low points of the surface. All surface elements of the controlled surface must be within this zone. The distance between the parallel planes is equal to the flatness tolerance value. The tolerance zone extends across the length and width of the surface.
The flatness tolerance is applied to a planar feature. You're correct. Each actual local size must measure between 29.8 and 30.2. You're correct. The flatness tolerance overrides rule number 1. You're correct. Click the right arrow to continue.
The interpretation of a flatness tolerance applied to a feature of size is significantly different from a flatness tolerance applied to a surface. Where a flatness tolerance at RFS is applied to a feature of size, the following conditions apply. Rule number 1 is overridden. The flatness tolerance value may be larger than the feature of size dimension tolerance. The tolerance zone is the space between 2 parallel planes. The distance between the planes is equal to the flatness tolerance value. The tolerance zone extends across the length and width of the feature of size. The derived median plane of the toleranced feature of size must be located within the tolerance zone. The feature of size must also be within its size limits. This figure shows you an example of a flatness tolerance at RFS applied to a feature of size.
The flatness tolerance is applied to a planar feature. You're correct. Each actual local size must measure between 10.1 and 10.5. You're correct. The flatness tolerance overrides rule number 1. You're correct. Click the right arrow to continue.
In this example, a flatness tolerance at MMC is applied to a planar feature of size. Where a geometric tolerance is applied to a feature of size at MMC, a surface interpretation, virtual condition boundary, is often used. In this course, the surface interpretation is illustrated for MMC applications, although a center plane interpretation may also be valid. Where you apply a flatness tolerance to a feature of size at MMC, the following conditions apply. Rule number 1 is overridden. The flatness tolerance value may be larger than the feature of size dimension tolerance. A bonus tolerance is permissible. Using the boundary interpretation, the tolerance zone is the space within the virtual condition, acceptance boundary. For an external feature of size, the virtual condition equals the MMC plus the flatness tolerance value. For an internal feature of size, the virtual condition equals the MMC minus the flatness tolerance value. Even though the flatness tolerance is interpreted as a boundary zone, it does limit the flatness deviation median plane by passing the feature of size through its virtual condition boundary.
The flatness tolerance value may be greater than the size dimension tolerance. You're correct. The flatness tolerance may be viewed as a virtual condition boundary. You're correct. The flatness tolerance does not override rule number 1. You're correct. Click the right arrow to continue.
Here's a simplified description of the verification principles and methods that you can use to inspect a flatness tolerance applied to a planar surface or a planar feature of size at MMC. When a flatness tolerance is applied to a planar surface, you measure the flatness deviation by finding the distance between two parallel planes that just contain all of the points of the surface. Your inspection method must be able to collect a set of points. Since a flatness tolerance is not related to any datums, care must be taken that the location or orientation of the toleranced feature does not affect the measurement. When a flatness tolerance is applied to a planar feature of size at MMC, the flatness deviation is often verified by passing the feature of size through a virtual condition boundary. There are many ways you can inspect a flatness tolerance. This course will explain 2 of them. Here are 2 common inspection tools you can use for verifying flatness deviations of a surface. Surface plate, a solid flat plate used as the main horizontal reference plane, datum feature simulator, for precision inspection and tooling setup. A surface plate is often used as the baseline for measurements to a workpiece. Therefore, the top surface is finished extremely flat, with accuracy up to 0.00025 millimeters for an inspection quality Grade A granite plate based on U.S. Federal Specification GGG P463C. Dial indicator. Also known as a dial gauge and probe indicator, it's an instrument used to accurately measure small linear distances and is frequently used in the inspection of parts. It's named so because the measurement results are displayed in a magnified way by means of a dial. Dial indicators are available for measuring distances from 0.25 millimeters to 300 millimeters, with graduations of 0.001 millimeters to 0.01 millimeters. Mount the dial indicator to the surface plate and set it to 0 at the level of the surface plate by using a gauge block. This establishes the reference plane, or the first plane of a tolerance zone, as you can see in this animation. Place the part on the surface plate, contacting its high points. As the part is moved randomly around the surface plate, the dial indicator traces a path across the part surface and measures the distance between the surface plate and the low points of the part surface. If the indicator reading is larger than the flatness tolerance value, the surface is not within its flatness specification.
When verifying a flatness tolerance, the flatness deviation of the surface is the blank between 2 parallel planes that just contain all of the points of the surface. You're correct. The flatness deviation of the surface is the minimum distance between 2 parallel planes that just contain all of the points of the surface. Click the right arrow to continue. A common inspection tool for inspecting a flatness tolerance applied to a surface is You're correct. A surface plate and dial indicator can be used to find the distance between the high and low points of a surface. Click the right arrow to continue.
Let's look at verifying a flatness tolerance at MMC applied to a planar feature of size dimension. The most common verification method used is a functional gauge. The functional gauge verifies that the feature of size does not violate its virtual condition. The distance between the sides of the gauge opening is set to the virtual condition of the feature of size. By verifying that the surfaces do not violate the virtual condition acceptance boundary, the flatness deviation of the median plane of the feature of size is also verified. You must verify the size tolerance separately.
Which method is valid for inspecting flatness applied to a feature of size at MMC? Incorrect. Only one of the choices above is correct. Try again. You're correct. A flatness tolerance applied to a feature of size at MMC results in a virtual condition boundary. Click the right arrow to continue. When verifying the flatness tolerance, what is the size of the functional gauge? You're correct. The size of the functional gauge is equal to the virtual condition of the feature of size, 10.9. Click the right arrow to continue.
These topics are recommended for further study to improve your understanding of the flatness tolerance. You've just completed the lesson on the flatness tolerance. If you're not confident in your understanding of these topics, review the information before proceeding. Close this window to exit the lesson.